Yes.
Good afternoon. Wow, it's so nice to see people. It's been far too long. Good afternoon. My name is Danielle Rod. I'm a director at the Swiss Polar Institute. And I'm very, very happy to welcome you today at this Swiss Polar Day. Due to COVID, we first postponed, then we changed plans a number of times, then we changed format. And with regard to COVID, of course, I should remind you to please respect all the rules you have received, the distancing in particular also during social moments towards the end. We have been very careful to try to maximize our chances of a very good event with a positive but not COVID positive outcome. So please help us. Thanks to COVID, maybe we should also look at the positive side. We are now in a blended format, and I would like also to wish a warm welcome to all our colleagues who are joining us online. And the great thing about this is that we have then friends and colleagues from all over Switzerland, but also from Montreal, from Paris, Cape Town, and beyond who are joining in today. So I would like to say a special hello to them. Thank you for joining. To participate and interact, for those of you who are in the room, well, please wave when there will be question times, and we will bring you a mic or help you with a question. Nina will do her best, and she will be around. So raise your hand. If you are online, during the Q&A sessions after the speeches, please write your questions in the chat, and we will read them out with a microphone here. During the open forum, please raise your hand and we will open your microphone at the end. Please really don't hesitate. This is supposed to be a lively meeting. I would like here to quickly thank the organizing team at SPI, Basile, Charmili, Laurence, Nina, thank you all. Thank you also to the team of Gabriela and to the whole team at the University of Zurich for your hospitality and for all your support. I know it's a bit heavy on the organization, these type of blended meetings. And talking about team, of course, well, we are not complete today. And we missed Connie today, Professor Konrad Stephan, who passed away in Greenland this summer. SPI was a bit his baby. So he was ambitious for us, he pushed me, sometimes out of our comfort zone, often. But he did this with this smile and this class that he had, preferably around coffee or a good glass of wine, and that helped a lot. He was ambitious for SPI, he was ambitious for the Swiss Polar Science, for all of you, and for our impact in society. And we owe it to him, I think, to do our best here. Thank you. Gabriela.
Yes, speaking about Connie, he of course was really much more important than just for the SPI structure and functioning, but he was really the integration figure for Swiss Polar Science and its community. He insisted with funders that the SPI should not be limited to the funding members only, but should be open to everybody, to all Swiss-based scientists. He integrated across scientific disciplines and beyond with policy, even with the arts. We all know that. He had always an open ear and supporting words and actions for early career researchers, but he was also always a good discussion partner with highly cited researchers. And of course, we all know that he had an overwhelming national and international network, and he's really leaving a big, big gap. But let's now focus also a few minutes on his scientific path. And Azuma Omura kindly was willing to speak to us for a few minutes and remembering Connie's scientific path. Please.
Ladies and gentlemen, In fact, I was not intending to talk on this topic today, but as all of you are informed, Professor Konrad Steffen abruptly left us 2.5 months ago in Greenland. And I would like to use this place to remember Konrad Steffen's contribution in science and to our society as a whole. It's not easy to do this in short time because as many of you know, Connie, so we called him, had a lot of assets. One is naturally scientist, and he was an outstanding educator, administrator, and also diplomat. So in view of the participants today, I would like to concentrate on his scientific achievement, and particularly as a legacy for young scientists. He accomplished many things in the polar science and also in a much wider sense, the science in cryosphere. But probably one can say at least there are two very important themes which he discovered, but not yet elaborated by the younger scientists. And one is the discovery of hot spots on the surface of the Polynya. Polynya is the surface of the polar seas, which open unfrozen during the whole winter. And there are two recurring large polynyas in the northern hemisphere, one north water at the northern end of Baffin Bay, and another one in the Gulf of Amundsen between Alaska and Canadian Arctic. And the reality of the Polynya was not yet known in 1970s, and that was the time Konrad Steffen stepped in as a doctoral work. And he, in a way, discovered, and I believe it is the first discovery of this hot spots open on the surface with a very hot temperature in the middle of the winter, +1 degrees. And that is 2.8 degrees warmer than the freezing temperature of the seawater. And that discovery turned the, at that time, accepted explanation of the existence of Polynya, namely that Polynya appears because the strong katabatic wind from Greenland will continuously sweep away the newly formed sea ice. So passively, warm water will be upwelling from the bottom, and that didn't work. There is definitely active flow of warmer current as a branch of Mexican Gulf Stream into West Greenland, and it comes up there. But how it comes up is not yet explained. So this is open for the future, Connie left. Another one is he established 17 automatic weather stations in Greenland. And Greenland ice sheet is made of, in fact, two ice sheets, main ice sheet to the north and southern ice sheet. These are quite independent from each other. And the southern ice sheet of Greenland is the ice sheet located in the lowest latitude in the whole world. And in many senses, that gives the image of disappeared Pleistocene ice sheets. So besides the contribution of ice sheets for current rising of the sea level, if some of you are interested in the process of disappearance of Pleistocene ice sheets like Laurentide, Phenoscandium, the southern ice sheet of Greenland will be a living example. And Connie set up 4 automatic weather stations there. So if somebody has an aspiration to connect the presently living ice sheet with Pleistocene ice sheet, there is enormous information. And there are many others which Connie left, but I will leave this to other occasions. Thank you very much.
So I think it's the moment just join me for a moment of silence in respect of Connie. Well, it was Connie's mission and vision that we should all contribute and make a difference, with small and large. And I think this is the mission we have to fulfill. And in this sense, I would like to continue with today's Swiss Polar Day and looking forward and ahead. And I now would like to welcome the President of the University of Zurich, Michael Hartmann, for a few welcoming words from the University of Zurich.
Grüezi miteinander. Dear members of the board of directors of the Swiss Polar Institute, dear members of the Science and Advisory Board of the Swiss Polar Institute, dear participants of the Swiss Polar Day. It's my great pleasure to welcoming all of you either physically at the University of Zurich or remotely via Zoom to this annual gathering. I can only second the extremely well-phrased words of Atsumu Omura on the passing of Connie. I personally had the privilege to be invited to follow up Connie in his function as director of CIRUS in Boulder. But a small university in Switzerland made actually a better offer. So I have been in close contact with Connie for more than 20 years. I will not forget our joint tour of Japanese research institutions exactly 1 year ago, where we had plenty of time to exchange ideas and shape future plans. It was exactly those moments where science was driving the thinking of Connie, not hampered by any administrative, technology, or other obstacles we tend to invent to prevent good ideas from happening. I'm personally very honored, and most of you may not be aware of that my regular office at the University of Zurich in geography is the former office of Connie Steffen, when ETH Geography was still located at the Ischl campus of the University of Zurich. So hence, I will never forget his legacy and strive to be as open-hearted towards science as he was. Thank you very much again, Omura-san, for your kind words. Future Earth, the World Economic Forum, IPBES and IPCC, with a little varying terminology, all agree that environmental risks will drive the global risk landscape in the near future. While all these undertakings agree that climate change and extreme events will be part of those risks, increasingly we recognize that land cover change, invasions, overexploitation and pollution form an inherent part of this environmental risk landscape. On short term, recent findings even argue that land cover and land use changes induced by human activity will outperform the impact of climate change. But maybe it's much more of interest to look at those risks that are not prioritized as substantial risk any longer, namely geopolitical, economic, and technological risks. They have seen much less priority than a few years before. I'm pretty sure you all may argue that at the poles, everything is a little bit different. Accelerated climatic change an increased number of extreme events, and even more geopolitical pressure drives the risk agenda at the poles with a different speed than maybe elsewhere on the planet. Therefore, I am very grateful that the Swiss Polar Institute recognizes these changes and supports polar research so powerfully and comprehensively. And as a geographer myself, I'm particularly happy to see that, so to say, old-fashioned expeditions are back on the agenda. Expeditions have become non-fashionable for a while, but are resurfacing again, as we will also hear later today. It is only expeditions that allow monitoring changes at the rate the change actually happens. We need to stress much more how important expeditions have become in times where science is dominated by in silico work. It is this unique combination of research methods and its holistic view on the changes in the polar regions that have also prompted the University of Zurich to join the Swiss Polar Institute as of January 2021. I personally wish the Swiss Polar Institute much success, and I'm very happy that the University of Zurich has committed to deliver its share to the Swiss Polar Institute, its mission, and to take on the responsibility to contribute to its success. I'm also very much looking forward to the upcoming program of today. I'm particularly curious about the fantastic contribution of Niklas Gruber on the ocean's carbon sink and the amazing experience by Julia Schmale and Martin Schnebeli during the Mosaic expedition. These are certainly highlights not to be missed. Let me close by thanking all those supporting the Swiss Polar Institute, either privately or institutionally. We all keep our fingers crossed that a third funding pillar, namely a governmental one, will follow soon. The Swiss Polar Institute fits, in my view, perfectly in the Article 15 funding scheme. So let's hope for a positive decision on that particular one. Ladies and gentlemen, despite the overly dominating C word, which I carefully omitted in my short introduction, I wish you a great Swiss Polar Day, and thank you very much for attending.
Thank you very much. This was, for us, a very positive message, and we are very happy that you are joining the family, and for all your positive words also on field work and the importance of actually being on site. I will start now this first part of the presentation on the Swiss Polar Institute to give you just some news. It's not the aim to make this an SPI day. It's not. But still, we have some things happening at SPI in spite of this year being a little bit different than we had originally planned, and therefore we want to share these news as well. We have a number of funding opportunities currently open or opening soon, so we take this opportunity to make sure that all of you are aware of them. For those who were not aware about the currently open calls, please hurry up. Deadline is Monday. For those who are more interested in the Polar Access Fund for Young Scientists, as every year, we will open the call in November, mid-November, and close it towards the end of January. In the documents you have received, there is a list of something we would like to push more and where we see great potential. However, this was definitely not the best year for it. It is the access of young scientists to field schools and summer schools in the Arctic mainly, and directly with some institutions which are really very involved in polar research. And we encourage you to pass this on to your students. This list is not exhaustive. If you have good ideas of other schools or courses that could be included, we are gladly including them. And we just wanted to also say a word about our arts and science program, PolArts, which is funded together with Pro Helvetia. which is currently a pilot program, but it's going very well, and we very much hope that we will be able to reconduct it in the future. And for those of you who wonder, what do these schemes actually look like and the projects that actually happen, then, well, we've used some of the time of this year in order to put a lot of examples, or actually all the funded projects on our website. And there is a very nice blog of field notes of those who are actually going in the field, who tell more personal experiences about what happened and how it went and what went well and what was more complicated. It's a nice read. So I encourage you to have a look there also to give you an idea of what you can do. In the health and safety area, I just want to remind you there are still, I think, 2-3 places open for this December's course. Hopefully it can take place in Sion, and the next one is, as usual, towards the end of March, April, the health and safety course in a cold environment, and it takes place near Sion. Something I would like to highlight is that we have actually purchased from a pharmacy in the Valais, a specialized pharmacy that can be customized for your expeditions that you can take along, and it goes together with training on how to use it and with courses for those who are going in the field. And this is a service that we think is really helpful, and we are gladly going to expand it if there is demand. And hopefully people can go in the field next year and use it. Upcoming events, just for your agendas, we have data management workshop that we are for the moment doing mainly for the grantees of the Polar Access Fund, but we are probably going to enlarge next year. So if there is demand, please let us know. We will set another date. We would like to organize, and there I would be interested in feedbacks, a webinar with a travel medicine specialist, Professor Janton from CHUV, about how to plan field activities in SPITE or in a COVID context. If you are interested, please let us know. We will organize this towards the end of January so that it can come in handy for planning the Arctic season 2021. And we want to have, as usual in the winter, an event specifically for social sciences and humanities interested in polar regions in Switzerland. We'll hear a little bit about that also towards the end today. And hopefully we can have a full Swiss Polar Day in April 2021 around Easter, probably as usual. Something that's close to our heart is a program we launched this year. It's the Swiss Polar Class, and I would like to mention it to you here because if you know either schools or courses or parents who are interested in content, this is actually a very nice resource with nice interviews, cartoons, explanation texts, which are customized on the Lehrplan that have been harmonized sort of in Switzerland. And so it's a nice resource, and we like it very much. So I'm doing a little bit of advertisement here. And now to come back to something a bit more serious, I pass the floor to Gabriela.
So, is this microphone still not working? Or is it better now? It's okay, good, thank you. Yes, so maybe you remember last year, those of you who were around, that we presented the Polar Science Plan that we developed over the actually almost years. With a lot of input by the scientific community, we came up with this Swiss Polar Science Plan that was also the basis for our application to the government to become an Article 15 institution. And you might also remember that we kind of identified 4 priorities, research priorities, one being cryosphere, the other carbon, nitrogen, water cycle nexus, biodiversity and ecosystem functions, and technology in extreme environments. This was the science outline, but then of course we understood very quickly we have to do something for the community. And the exciting news is that actually we have worked hard on it, and we came up with these flagship initiatives. The concept is that it will be polar programs, depending on Article 15 funding. It will be 1 or more for Swiss polar research. the idea is to have multi-annual larger research clusters. So it's not projects for single research groups, but it should really be kind of a cluster approach. And they should be based on one of the 4 scientific pillars of one of the 4 topics we identified in the Polar Plan. The funding will be focusing on field campaigns, data management, outreach publication, program coordination. It's not thought for scientific analysis, so you cannot fund your postdocs and PhD with that money, but you will be able to fund at least 2 field seasons with about 400,000 francs. That's kind of the core funding that will be available. And then if the government is favorable for polar research, this will be even extended towards 2 flagships with substantially more contributions. So this is really your opportunity, and I will just tell you a little bit about the time plan now, so you can start to prepare and think about what you could propose. So the total funding level and duration is still to be confirmed. So what I told you right now is really kind of the lowest, the minimum that will be available. The call for proposals is foreseen in January to February 2021. So you can already start to discuss with your colleagues. You're really invited to do so. And we'll have a 2-stage proposal process. There will be a deadline in spring for the pre-proposals and then in late summer. And to support you, we will plan for those projects that went successfully through the pre-proposal stage. We plan collaborative workshops, so you can really come together with your colleagues and discuss your full proposal. The selected programs will then be evaluated by an international panel following the regular peer review process. And then people will be notified by about end of 2021 whether their program, their research cluster will be funded or not. This is the schedule. You don't need to read through everything. All this information is now, from now onwards, available on the website, on the SPI website. If you go under the bar at the tab SPI funding, there is a tab SPI flagship initiatives, and also a PDF file is available there with all the information, so you really can start preparing. Important in this document, you will also find the categories of funding, so what can be funded through the flagship initiatives. Well, we really hope that we will get a few good proposals in. We will get 1 flagship in the end, at least, maybe 2 running over the next 4 years. But we really need very good proposals. So we urge you to sit together, to think about what you can propose that is really exciting, so we have something to evaluate. Then just a short update on the structure of SPI, a short reminder how we work. We have, of course, a board of directors, then a science and technology advisory board that I'm currently chairing, and of course, the scientific director and the executive director together with the SPI secretariat that run the SPI. If you have any concerns from the science point of view, you can always contact the STAB, so you can also contact just me directly or the SPI secretariat. And the board of directors will soon launch the search for a new scientific director. This might also be an opportunity for some people of you. Just a small update on the Science and Technology Advisory Board, so you know who is thinking about what science could potentially be done at the SPI or facilitated by the SPI. So this is the list of people that is also available on the website. We had a few members that rotated out. Thomas Stocker left, for example, but also Karin Lochte arrived at the end of her term and they stepped down. So currently it's myself chairing the board. My background is in ecology and earth system science. Then we have Björn Dahlbeck, who was a former director of the Swiss Polar Research Secretariat, so a very similar structure to the Swiss Polar Institute. His background is in marine biology, and he is the vice chair. Then we do have Jane Francis, who is supporting us in the STAB. She's also an ecologist, paleoclimatologist by training, and she's also the director of the British Antarctic Survey. Then we have Philippe Gier. He is affiliated with EPFL and also very much in the digitalization of things. So he really supports us with the technological aspect as well. Then Frederick Herrmann, you might have heard that he was nominated to become the president of the University of Lausanne, but he's still with us working on Earth surface dynamics, and he certainly also provides the link to the high altitude research community. Christian de Marliev, he is representing Edition Posen. He's really the guy you want to talk to when it comes to field logistics in Arctic and Antarctic. He's super experienced. And then Heini Wernli, who is with us today in this room as well on atmospheric sciences. And finally, Hubertus from the University of Bern. He is also representing the Swiss community through the academies. And this is the same for Patricia Holm. With this, I would just really like to ask you to stay in touch and do not hesitate to contact us, to inform yourself. And we would go now on towards the more interactive phase of this Swiss Polar Day. Yes. Are there any questions at this point? Of course. Maybe also from the chat, if anybody who is online has questions.
Good. So now, moving to the science part of our afternoon, I would like to introduce, if it's needed at all, Nicholas Gruber, our keynote speaker for today. Thank you very much, Nikki, for accepting our invitation. Maybe postponing was actually our chance in the end to manage to get into your schedule. Nikki is a professor at ETH Zurich. He is notably there, he heads the Center for Climate Systems Modeling, amongst many hats. In his own research, he focuses on the study of biogeochemical cycles in various timescales and on various geographical scales, as I could understand and try to summarize. From his impressive CV, I would like to maybe underline one thing. It's his strong involvement in international groups, in particular in IPCC work. And I think we should never cease to underline the importance of such work and such groups. We are very much looking forward to your talk. The floor is yours.
Thank you so much, Danielle, for the introduction. It's a big pleasure to be here and talk about the Southern Ocean. I'd like to take you on a journey to this fantastic, but also a bit fearful place. This is a wonderful image put together by NASA, showing essentially the complexity of the Southern Ocean, showing the main players, the Antarctic continent, which is a very important element for driving the systems, both in the atmosphere and the ocean. We see the sea ice, we see the clouds and the continents. It's a place that has fascinating people all the time, but it's also a place that we have some fear to go to. I mean, it's holding 60s, screaming 60s even, is one of the descriptions that the sailors have given to this place. So not necessarily a place that everybody wants to go to. It's definitely one of the big frontiers in research. It's a place that not many people have seen, myself included. I've never been there, I have to admit. but it's definitely a place I want to go to, even though I get seasick and I'm a bit fearful as well to go these places. Anyway, so today I would like to talk about the role of the Southern Ocean in the climate system, and in particular, the role of the Southern Ocean for the global carbon cycle. And there's one number I would like to bring up right away. It's 1 billion. And this number is important because it's 1 billion tons of CO2, or excuse me, 1 billion tons of carbon that displace the Southern Ocean. And the region I'm talking about is the region of south of 35. We have a relatively generous definition of the Southern Ocean. That's the amount of carbon that this system is taking up every year. And that's a big number. If you take a cost of CO2 at the moment of about 10 to 20 euros per ton of CO2, or you take even the 100 Swiss francs per ton of CO2 that we actually have in the CO2 law, then that number translates into 400 billion Swiss francs a year. That's the amount of ecosystem service that this place is giving to humanity by removing that amount of carbon from the atmosphere every year. That's a number, 400 billion Swiss francs a year. And so if we talk about funding research here in Switzerland on maybe at smaller levels to go to these places and better study and find out what they do to us and whether that ecosystems will continue into the future, I think it's peanuts relative to the ecosystem services that these places are giving to us already. And I think that's a very powerful statement about why we need to go to these places, measure it, observe it, and also model and better understand it. And that's kind of the message I would like to give across to do today. So this is a talk that, of course, I have to rely on many people, and I would like to particularly thank two individuals. Peter Landschützer, who was a postdoc with me, is now at MPI, has done a lot of work on the analysis of the PCO2 observations that will show. And Alex Haumann, who is a PhD student in my group, has done a lot of modeling work and also has been a winner of the prize from the Swiss Polar Institute. Thank you for that at the time. So what am I going to talk about first? I would like to highlight really the importance of the Southern Ocean for the global climate system, and particularly its contribution as a carbon sink. So I would like to show to you where this number of 1 billion tons of carbon per year is coming from. And then I would like to show you some results of recent work that has shown that actually this ecosystem service is quite variable, much more variable than we had thought. And that it would indicate a certain vulnerability. That means that we cannot take for granted that that carbon sink will remain there forever and help us into the future indefinitely. And I would like to close also with some of the challenges we have. These are places that are not well observed, and some ideas how we can advance on these observations. I will show some research that it's mainly done actually in the United States, not by us. But I think it's very inspiring, and it could serve as a role model for also some work here in Switzerland. Okay, so maybe just to illustrate just at square one, what is the role of the ocean, not just only the Southern Ocean, as a sink for CO2. So every year, and these are the average numbers for the last decade, we're emitting about 11 billion tons of carbon. Majority comes from the burning of fossil fuels, but a significant amount also from land use change. Where does the carbon go? 46%, as we know, accumulates in the atmosphere. That's a number we know very, very well, thanks to lots of measurements of atmospheric CO2. But we also know that about 24% goes into the ocean. That's the big ecosystem service that the ocean is providing. But it's also a very significant fraction goes into the land. So both land and ocean are extremely helpful to us. But today I'm going to be focused on the role of the ocean. So why is the Southern Ocean so important? This is some work that Thomas Fröhlicher did based on models. And what he looked at on the basis of these models is between 1870 and 1995, how much carbon are sort of broadband regions in the ocean taking up. Now, I hope this is working with the pointer. Not quite. Okay, so I'll just describe it. So what you see on the left-hand side is the ocean uptake of anthropogenic carbon and separated in latitude bands. So this is between 90 south and 30 south, and then the tropics and the northern hemisphere. And what you can see, and we just focus right away on the region south of 30 degrees, that of all the carbon that is taken up by the ocean, 43% of the global ocean, as global uptake is occurring in the Southern Ocean. And if you put this in percentage, it's only 30% of the global surface ocean, yet it takes up 43%. As a matter of fact, for heat, that asymmetry is even bigger. 75%, a whopping 75% of the global ocean heat uptake. And that's, again, a major ecosystem service that the ocean is doing to us. 75% is taken up south of 30 degrees. Well, you can say, well, that is models, huh? You know, models have their errors, their mistakes, their biases. So can we see this in observations? But before I show the evidence that we have based on observations, I need to take a step back quickly and talk about the different components that actually drive the ocean carbon uptake. And in this figure, I kind of have two sides of the coins of the carbon. So there's only one carbon molecule, one type of carbon, but we can distinguish kind of the sources of where the carbon is coming from. So we have this anthropogenic perturbation, the extra CO2 we add to the atmosphere from the burning of fossil fuel and land use change. That's the left-hand side. That's the anthropogenic carbon component, the extra carbon we put in the system that gets redistributed. And the Southern Ocean is just a sink region, a more enormous amount of anthropogenic is carbon taken up, and that's what Thomas Fröhlich talked about in his paper. There's also the natural carbon, the carbon that has been there forever and has been cycling between the atmosphere, land, and ocean. And the Southern Ocean is a bit more varied contribution with regard to natural carbon. In one hand, it's actually pretty big, important sink regions towards the more northerly latitudes, essentially north of about 45 degrees. It's a very important sink region, but it's also a source region at the higher latitudes. And that matters when we start to think about how climatic variability will impact the carbon cycle, because it will have different impacts on the two components. And I will show later that when it comes to variability, it's particularly the thing on the right-hand side, the natural carbon cycle, that gets impacted. Okay, so what type of observations do we have available to say, okay, well, the Southern Ocean is indeed a very important carbon sink? Well, there are two types of observations, but today I'm going to show you just one of the evidence, the pieces of evidence, and that's based on surface PCO2 observations. So we measure and the CO2 concentration in the surface ocean. That's done today largely by ships of opportunity, ships that essentially serve goods and travel around the ocean that we put instruments on. And in the Southern Ocean is primarily done by research ships that have been instrumented since sort of the late 1990s with such instruments. And you can see that the routes where we have observations reflect essentially that distribution of where there are ships. So the supply routes to Antarctica are well sampled. Other places are much less well sampled. A big hole is, for example, the southeastern Pacific. You can imagine that these white spots have never been measured at all with regard to the carbon content. So the huge gaps. This is the total amount of observations. We have a total about 28 million observations. And that's the snapshot of all of the observations we have. Well, how can we make use of those observations? And together with Peter Landschütz, we've developed a machine learning methodology that allows us to take those in the overall really sparse observations and interpolate them to the globe in order to essentially depict where are the sources and sinks of carbon. And this is our reconstruction of the Southern Ocean carbon sink. And as you can see, it's not just the carbon sink, it's actually, the whole thing is breathing carbon out, in and out again. So what you're seeing is actually not the flux, it's actually the surface partial pressure of CO2. And whenever that surface PCO2 is above the value that you see at the bottom, which is the atmospheric CO2, as we're marching through time here, that it's increasing. So whenever the value is above that, the ocean is exhaling CO2, and whenever it's below that, the ocean is intaking CO2. So the Southern Ocean is breathing like a lung, huh? So CO2 in and out. And what we're going to be talking about is really the net fluxes, what is left over at the end of the year. So the ocean is like land, breathing carbon in and out, And you see now as the animation is progressing that overall the PCO2 level has gone up. The colors have turned more yellow and reddish comparison to the beginning, because as the ocean is taking up net carbon, its concentration is increasing through time. And that's essentially a reflection of the sink that I just talked about. So you see now at the end of the simulation, we're really now in the reddish zone of the system. And from this, we can actually then infer what the variability of the carbon sink actually looks like. And I'm starting here with the estimates for the 1980s. And in red, you can see the contribution of the Southern Ocean to the global carbon uptake. And it's 60% of global carbon uptake during this period actually comes from the Southern Ocean. The Pacific and Atlantic Ocean, and we're taking the boundary here at 35 south, are contributing the other 40% of the system. And by the way, now in the context of what I said before, this is the total uptake, anthropogenic plus natural together. Well, how would you expect that carbon sink to develop through time? Well, as we put more CO2 into the atmosphere, you would expect that the uptake by the ocean will increase commensurably. You just push more CO2 in the system, into the atmosphere, and that pushes essentially more CO2 into the ocean. That's kind of what you expect. So the question is, well, has it actually increased accordingly? And that's the next topic. And in 2007, a colleague of mine, Corinne Lecqueret, published really a very influential paper where she used models and atmospheric CO2 observations to say, well, probably not. The Southern Ocean has not increased as expected. And so this is again the red line. You see there's two times you kind of see the same thing, just two different ways of showing it. The red line is what you expect. And what I forgot to say, negative numbers are uptake. You know, just make sure that we're all on the same page with regard to the sign. So the red line is what you expect, the same what I showed you before, the dashed black line. And then the two lines, the blue ones at the bottom is an ocean model, and the other ones is atmospheric CO2 inversions. So constraints we have that they have obtained by using atmospheric CO2 observation both show that the uptake has not increased as expected, has stagnated or even weakened. And so they talked about the saturation of the Southern Ocean carbon sink. And if that's true, and if that continues into the future, that's bad news, because that means we cannot take that Southern Ocean sink for granted as we go into the future. So the question is, what do our reconstructions say? Well, indeed, for the 1990s, our reconstructions confirmed the model-based results of Corinne Lecqueret and her colleagues, that indeed a significant reduction of the global uptake, and that significant reduction comes primarily from the Southern Ocean. So indeed, this probably has happened. So why did the Southern Ocean sink decrease? And the interpretation that we have is that this is due to an increase in the winds and also a poleward contraction of the winds that led essentially to increased upwelling of carbon-rich waters from mid-depths to the surface, and that pushed essentially extra carbon out in the system. This is primarily this natural carbon cycle that was impacted. So it's a change in the winds, the change in the climate system over this period. Part of it is probably due to changes in the ozone hole even, that led essentially to that decrease in the carbon uptake in the Southern Ocean. So the question is, what about the period post-2000? Well, our reconstructions say, well, we had a rebound, we had a reinvigoration, as we called it, of the Southern Ocean carbon sink, a whopping about more than twice increase of the carbon uptake in the Southern Ocean after 2000. And that brought essentially the Southern Ocean carbon sink back to the expected, which is good news. But at the same time, it also shows that we have significant variability of the sink, and that future climate change could actually have a significant impact on that carbon sink in a way that we have not fully understood yet. So why has it increased again? You would think, well, just the winds went back to the original position and weakened, and that would have helped, but that's not what happened. Actually, during the post-2000 periods, the winds actually started to become much more wavy. We have a much more sort of undulation patterns of the wind systems over the Southern Ocean. And that led to complex, actually, interaction with the surface ocean and the carbonate system. So in the Pacific sector, for example, we continue to have anomalous upwelling, but that was overcome by very strong cooling, some of which can actually be related to sea ice, as I will show in a minute, but also changes in circulation in the Atlantic sector. And all of that together led to a relatively complex response that I don't have time now to go into details, but it shows that it was not just simply symmetric. It was a much more complex response, but it shows all the also fascinating interactive elements that we have to take into consideration when we want to understand the ocean carbon sink. So I mentioned sea ice. This is some work by Alex Haumann, and we have shown that we have had a significant change in sea ice, and not only in the distribution of sea ice in the Southern Ocean, but also in the sea ice transport. That sea ice that forms near Antarctic continent is being pushed out in the Southern Ocean where it melts. And that is a significant transport pathway for salinity. And we have published recently at the summer paper where we've shown that this actually led to cooling, and it's a major contribution to cooling in the Southern Ocean. And that has an impact on the carbon sink, because as you cool the water, you take more CO2 from the atmosphere. And we've done some simulations with our model and showed that indeed we can actually, particularly in the Pacific sector, that a part of that uptake that we have seen post-2000 can actually be related to changes in sea ice and sea ice transport. And then we also did simulation looking at the impact of wind. That also has a contribution. But again, that just illustrates it's a pretty interesting, complex, interactive system that we're talking about in this place. Okay, I skip this and then goes right away to challenges and opportunities. All of that, what I showed you, you can take, one has to take with a big grain of salt. Because if you actually look at the observations that we have available to reach all of those conclusions, it's not overwhelming. So this is a number of observations we have in the 1980s and 1990s. We're showing all observations in that decade. And then you look at, you go further, even between 2010 and 2017, we have many places which are blue, which mean have only 2 months of observations, 2 months in 10 years. And then the Drake Passage, for example, has very good coverage. So we have a hugely undersampled problem here. So how can we move forward? There are multiple pathways, but one that I'm particularly excited about is the progress that our community has made of instrumenting autonomous platforms with modern sensors. And these are sensors that can measure oxygen, that can measure pH, that can measure ocean color properties, and nitrate these days. And a consortium in the United States, led by my postdoc advisor, Jorge Sarmiento, has put together this fantastic program, the SOCOM, where they have now started to deploy such instruments in the Southern Ocean. And they, within 2 years, they have sampled the Southern Ocean more than has ever been done before cumulatively. And so that's the type of revolution I think that we need in our community if we want to make progress to actually and really go there, because we can't afford to have ships there all the time. So we need autonomous platform. And I think this is one, not the only one, but one of the options available to us. And just to show you kind of the different picture that you get. So the blue and the green lines are two of these estimates. The blue one is the one I just showed you. And then for the new observations that have now come online, this is work by Seth Boshinsky from Princeton, have shown maybe what we're seeing here in terms of a huge carbon sink may be not right. And if you look at where this difference is coming from, is from the winter. We have no winter observations today. And these floats are the first time we have actually winter observation. So maybe we're completely wrong. And I don't know yet whether we are wrong, because these floats still have technical problems. There are uncertainties in these measurements. They're not measure PCO2, but it shows you that we have not solved the problem yet. And I think going there, making these measurements, really second what Michael Shetman said before, we need to go these places. Modeling is what we need afterwards, but we need observations in the first place. And I think it's a fantastic opportunity here with the Swiss Polar Institute that we can do these things. And I hope that as a Swiss community, we can really make a significant progress in that direction. So I close here with the key points. So the Ocean is an important carbon sink. It's variable. And I think we have fantastic technological opportunities ahead of us. And with that, I would like to also give a short tribute to, to Conny. So I had the pleasure to work with him over the last few years in the context of the special report on ocean and cryosphere. And so it was just a fantastic endeavor to work with him and enjoy time. So thank you. I think there's room for questions. Sorry. Yeah.
So thank you very much, Vicky, for this very interesting presentation. Completely layman's question. What's the carbon uptake of a frozen ocean surface? Is there any, or is it moved away to the open water?
It's not a trivial question, as you might think. So the first instinct would say, well, if you have sea ice, there's very little transport of gases across that because, I mean, there's really a very strong physical barrier. It turns out that actually fragile sea ice is actually more conducive to CO2 transport than one would think. And there's some excellent work by people in Canada and other places that have actually shown that there is transfer across sea ice. I think the more relevant actually transport occurs more in Leeds and Polynias, because I mean, Muro-san talked about Polynias before, and in the same way as they're massive hotspots of heat transfer, actually they're massive hotspots of CO2 transfer, in a way that we actually don't know, because we have rarely measured them. And so essentially what happens in between the sea ice, I think is probably in the end the more relevant piece. And it's particularly sort of in springtime when the ice breaks up, and perhaps also during the freezing period, where there might be significant fluxes that we really at the moment don't have a good handle on.
I have a mic, it makes your life easier.
You have an advantage.
You focused on obviously on the Southern Ocean, and the Argo float there is particularly precious because access is so difficult. Do they use Argos in other places? And that's the first part of the question. And then how does one link a campaign with Argos and their SOCOM program?
Okay. So the first question was about other places. So SOCOM focused primarily on the Southern Ocean, but there are other programs where people have started to implement and deploy such floats. And I mean, we're trying to build essentially international community of the biogeochemical Argo program and try to sell it. I think at the moment, there are about 130 floats from SOCOM out there. There are about another 150 floats out there in other parts of the ocean. And we're trying to build now sort of the framework, the data streams and so forth, data quality centers. But we, in that program very closely collaborates with the standard Argo program that focus primarily on the physical oceanography, the temperature and salinity, because they're so complementary to each other. Yeah, Gabriela.
So you mentioned in situ observations, probably then really going deep down into the water, and you mentioned modeling. You did not mention remote sensing observations that could play a certain role. How much information can you really get from surface measurements that are being done by satellites?
Well, again, I mean, the remote sensing component is extremely complementary. I didn't say that, but for example, this reconstruction that I showed with this machine learning approach relied very, very heavily on remotely sensed observations. So we used sea surface temperature for that purpose. We used chlorophyll, remotely sensed chlorophyll for that purpose, because the role of biology in driving some of the seasonality we see, also year-to-year variability. And more recently, in we're also using now sea surface salinity from space. And we've also tried around with sea surface height and other parameters. But yes, I mean, without the remote sensing, we would not have that coverage, that synoptic coverage that we need in order to essentially extrapolate the individual observations to the area. And I just like, I mean, salinity is an interesting parameter actually for the carbonate system. And there's actually quite a bit of good hope that this really helps actually us to not so much looking at the large scale pattern, because that's well understood, but more the fine scale patterns in the system.
Hello, thank you very much for this nice presentation. And you've got some nice eddies showing in your animation. And I was wondering if those mesoscale feeder play an important role at the level of the Southern Ocean.
Mm-hmm. Well, the simulation sort of is, first of all, maybe just a quick explanation. This is a high resolution simulation done by Alex Howman with our model. And it starts actually from rest, and then what you see is spinning up the eddies. And of course, you see the ACC structure here, the Arctic for color current, and it's kind of very detailed structure with the mesoscale variability plus the storms passing through. That's the impact on the sea surface velocity from the storms. Yes, mesoscale eddies is a topic of great interest to my group and myself. At the moment, the focus is much more sort of on the integral effect of eddies. So in what way do they change the circulation dynamics? In what way do they change biological productivity patterns? If you go there, of course, if you cross one of these eddies, you see massive excursions, of course, in the CO2 system and any other parameters. We know that some of the eddies are hotspots of biological productivity and others are actually deserts of biological productivity. But the question is how much of that is just noise and averaging out, and how much is there a sort of an integral effect of those eddies? And some of our work, we have actually shown there is indeed a significant sort of cumulative effect. This is not just noise, that actually are an integral component of the dynamics of the system, both regard to physics as well as biogeochemistry. But again, it's not something we have fully understood yet and fully grasped in all aspects. And that's why we continue to push very hard for such high resolution simulations. And it's also its interaction with the atmosphere.
There's a question from the chat online from Jan Kasper Platner. First, he thanks you for your presentation and he shares your feelings about Connie. He wants to ask you, you mentioned the challenges in terms of observations, the uncertainties associated with them, and need for new technologies for data from Southern Ocean. What do you see as biggest challenges and necessary next steps on the modeling side?
So I think the biggest step, I think, on the modeling side is really the atmosphere-ocean interactions. I mean, this is something I share with Heini Wernli, because both at the local level, it comes back to this question of mesoscale, because there's a significant coupling of the atmosphere and the ocean at mesoscales. The currents that we see here have an impact on the atmospheric dynamics. And that's something we haven't really fully grasped. And then those elements have changed essentially the heat fluxes, momentum fluxes between the atmosphere and the ocean. And I think trying to understand how that system really works as a coupled system, and then include on top of that the interaction with sea ice and maybe partly even the glaciers, the melting glaciers and all that contribution. I think I would say the thinking in terms of the coupled system and what it does in terms from time scales of weeks to months, but also really the centennial time scale, I would say this is really the biggest challenge that we have at the moment.
Oh, no, it's not working. Yep. Just press the button. Yeah.
Otherwise, I can just repeat it. That's.
Okay. So following up on the challenge question, so you mentioned that the floats actually don't measure PCO2. A very ignorant question. Why not? What's the problem?
Well, so what they do measure is actually the pH in a very interesting way, by the way, so some form of resistor. So far, we haven't found a clever way to develop a system that is robust, stable, low power consumption, and also doesn't drift. I mean, you have to, there's a lot of conditions that you have to fulfill in order to be able to deploy a system remotely for 6 to 7 years, and all there is. So far we measure CO2 mostly by equilibration. So we take a water sample, equilibrate with the air, measure the CO2 in the air. We know how to do that very well. But you can't miniaturize that, because if you try, that is already a very bulky system. We have some autonomous surface drifters that actually use some of a similar technology for that, but to miniaturize in the sense that you can put it on a float is very, very hard. There are attempts to develop other sort of types of systems through semi-permeable membrane systems and so forth, that you can really look at very tight and small sensor systems. At the moment, the trouble that we have right now with those sensors is they're very slow in responding to the gradient. So the diffusive time scale across the membrane just takes minutes, and the float we usually would like to go up and down with a decent speed across gradient. So we need, for the sensors to be useful in the current configuration, they need response time scales of seconds to a few seconds. So that's yet another very, very, very hard constraint on the problem. And that's, but I'm hopeful that we eventually will. I believe in creativity of people and Okay, thank you so much.
Very much.
And also thank you for the big, excellent question. Thank you.
Thank you very much. Sorry, all this disinfection system is taking a bit of logistics. So we'll just change. Oops, where is it here? Can you put it on the first, please? Thank you. Sorry about that. So I would like to now introduce an actually changing hemisphere, staying on oceans in a more or less icy state. I would like to introduce Julia Schmale and Martin Schneebeli. They were very lucky this year. They had a close escape, but they managed to actually go on probably one of the most fragile expeditions that could have been set up in those circumstances, and they managed an amazing work of logistics and resupplying throughout the whole year. So an amazing job by our colleagues at AVI. Julia is a tenure-track professor at EPFL. She's the head of the Extreme Environments Research Lab, EERL, in Sion. Her work focuses on atmospheric science, in particular on the role of aerosols. Martin is a very different field. He comes, he's a group leader, snow and permafrost at SLF in Davos. He's a recognized specialist on snow, basically in all its states, if I may say that. What they have in common, many things I'm sure, but this year is that they both were Swiss participants and PIs on the Mosaic expedition, which just came back successfully this week. Julia led the Swiss aerosol project Embrace, and Martin was PI on the Snow Mosaic project. Together they will tell us about their science there, but also their experiences. And if I believe the amount of megabytes of your presentation, I'm sure we'll have some amazing pictures. Thank you.
Yeah, hello everyone. I hope the microphone works now. Yeah, so it's the pleasure of Martin and me to give you a little bit of our personal insights into the Mosaic mission, and maybe a bit of a disclaimer. This was not supposed to be a scientific presentation, but if you ask two scientists to give a presentation, there will be a bit of science. So we hope we made a good mix. So yeah, I'll just start to tell you what Mosaic actually is. This is an idea that came about 11 years ago in 2009, where we had a first meeting in Boulder in the US. And the idea was to have a multidisciplinary drifting observatory to study the Arctic climate. And on that slide, you see the concept behind it. So the drifting observatory is an icebreaker, in that case Polarstern, which you see in the center of the flow. And then the multidisciplinarity comes in by the different neighborhoods you see on the ice. So there is Ice City to take snow samples or drill ice cores, sea ice cores. There's Ocean City to do CTDs, to let a remotely operated vehicle down to the ocean. There is Met City to measure meteorological parameters, to launch radiosondes, operate tethered balloons, etc. And then the Central Observatory itself hosted a bunch of heavier instrumentation that you might not want to put on the ice, and later on you'll see also why. And then, of course, we needed a very strong logistics team to make all of this infrastructure and operating the infrastructure on the ice possible. And then this shows you the drift track. Not sure if this, the point, well, anyway, so we started in Tromsø 1 year ago in September, and then moved to the Russian Arctic Ocean. And this is the black star you see, and then we drifted, and you see that sometimes the track goes out of the ice and back into the ice, and this is due to the complex logistics. So here is a bit more of a schematic. So we started last year, then moored the ship to the ice and drifted with the ocean, the sea ice current. And the detailed process studies would happen all around Polarstern and on Polarstern, but then we also had a distributed network, which you see on the upper right. And this is distributed roughly 50 kilometers around the ship, and that should represent something like a grid box in a model. So we would have multiple measurements within such a grid box. That was the idea, and these measurements were operated more or less autonomously. So that just basic variables, temperature, relative humidity, radiation, and so on, that you can measure alone without people attending these instrumentations every day. And then there was also the idea for a larger scale connection with the aircrafts on the bottom left, one mission in spring and one mission in summer. And then there is a station network around the Arctic, which you see with the red dots, where there is permanent observation, so we can also connect to these. And since the expedition was more than a year long, we also needed to exchange scientists and the crew. So the idea was to have 6 legs, 2 months roughly each crew, and they would be exchanged with different international icebreakers. So it was a big international effort. But then obviously we had something we could not foresee within the Mosaic planning, that's COVID-19. So some of the things actually had to be changed. And the first thing is the ship actually had to leave the ice because it was not possible to have people brought in with a different icebreaker or aircraft during the lockdown period in spring. So this was the first big change. The change that went hand in hand with that was it's not 6 legs anymore, but 5 legs. So people who were on board from January and were supposed to go back in April had to stay till June. And I was one of the people actually experiencing that. And then also the aircraft campaigns could not happen. So the spring one did not happen. And then in early summer, they did a couple of flights to survey the sea ice, but that was way below the scope of what was planned beforehand. But nevertheless, I think it's actually quite amazing. And we owe a huge thank you to Avi to actually run this expedition through the entire year. I think this is anything but for granted. And so I think all of the scientists and particularly those PhD students and postdocs who depend on the data will be very happy for all of these efforts. And so, I mean, it's a lot of effort, it's costly, it also has an environmental impact. So why actually do we want to study this? So we heard about very important issues in the Southern Ocean before. These are now important issues for the Arctic Ocean. You've probably heard of Arctic amplification that's shown with this global map here, where you see a temperature difference between 2019 and 1960. And you also see that the Arctic is basically the reddest place on Earth. So that means the temperature change there is the largest. And if you look at the curve at the bottom of the panel, that's by latitude, you see that these temperature differences are much higher towards the Arctic region, so beyond the polar circle than anywhere else on the globe. And on average, the Arctic is warming 2 to 3 times more than the rest of the globe. And while we know quite a bit about it, why that is the case, we don't know all of the contributing factors, and we also don't know their relative importance. So this was one of the things we definitely wanted to study there. And then one of the features how Arctic amplification manifests itself is with the sea ice retreat. You see with the pink line here, the September extent of the sea ice between the 1980s and 2010 in the median, and then actually what we observed this year. So there's a significant shrinkage. And if you compare the curves from several years, you see the average over the decades in the gray. The dashed line at the bottom is the worst year ever, which was 2012. And this year, when we were on the ship, actually, partly we were even below that curve. So that's the green curve that you see. The absolute sea ice minimum in September was less severe than in the previous years, but it was actually very interesting to be out there when you experience such extreme conditions. And with that, I'd like to hand over to Martin.
Thank you. Thank you, Julia. You may wonder why we work at Polar Night. And as a snow scientist, snow is the insulator of sea ice. And there are, logically, when you see this picture, not that many measurements at Polar Night in the high Arctic. Our goal was to measure the snow properties with as high resolution and as many instruments as possible. Oops, that's the big one. So I show you now a short movie of our work at Polar Night. It's not in real time, it's in high speed. And now I have to find out how to start, maybe like this. Yeah. So that's a snow pit we do on sea ice. These are samples for our microtomography. That's the special thing with the Polarstern. We have really a very excellent laboratory where we can put instruments which are otherwise impossible to bring to the Arctic. And here we return the samples to our home base, the Polarstern. You can imagine it's not that fast. It usually took 2 to 3 or 3 to 4 hours. And that was really about the limit you could work in the field continuously lying on the ground and in the wind. So the typical wind was about 10 meters per second and sometimes more. So as you can imagine, I was on this leg 2 at Polar Night. Now, what can we see? And why do we this work on the Polarstern during the entire year? I mentioned, and that was this maybe a bit funny looking coring of snow pieces in the movie. We have a X-ray micro CT on the ship. So we can image a 80 millimeter core with about 30 micrometer resolution. So really at very high details. And the images here, it's a time series now from the wintering in again at the end in September. So winter starts in this latitudes in September. You see the very fast change of the snow surface. So that means very different reflective properties, very different also reflection of remote sensing signals. And that's essential to understand where and how the Arctic changes and then to drive the complex models Nicola showed us. We also measured during summer, and is sea ice not just ice? Sea ice is a very strange material because it has small channels of brine. So when it melts, it doesn't melt like a flat ice surface. It disaggregates into these huge crystals, sometimes called Jewel crystals. They have a very strong influence on the reflective properties, on the albedo of the snow. And that's the first time we could really investigate these properties in detail and over this time. You see, there are also now in summer, there are different challenges. You don't have the cold, you don't have the frosted face, you have the ponds. And my PhD student, Amy McFarlane, was involved actually in leg 3 and 4, and she illustrated what happened during these legs very nicely. So during leg 3, the left picture, the flow broke up. That's this huge crack. So you had to deal with all this dynamic of the sea ice. And also for me, even in winter when it was very relatively stable, sea ice is extremely dynamic. And you could start at one end of a flow and then the bear guard would call you and you are on a completely different location. So what we have achieved, so we have terabytes of data from the CT. We have really a lot of field observations during the entire year. And I think that's one of the main achievements of Mosaic, that we have not only snow, but we have oceanic fluxes in the sea ice, this small snow interface, all the atmospheric fluxes with all the chemical components Julia will talk about. And now something entertaining. There are also animals, and it's actually very interesting. How do they move? And that's in real time.
Did you have polar bear visits?
No, or we had one, but only at night, and we only saw it by a camera. Mm-hmm. But then we saw this polar bear when we returned with the Daranitsin.
Yes, yeah. We also had just one polar bear visit in spring on 26th of April. And I remember that because it was before 6 in the morning. And I shared the room with the head of logistics, and they called her because she was also the chief polar bear guard and had to deal with the bears. So we got very, very frightened voices from the bridge calling us over the telephone quite early. So we got a couple of nice shots of them. So I wanted to explain a little bit how we exchanged between the legs. And this is now basically Martin's crew going back to land and us going to Polarstern. And this was during Polar Night. So we left Tromsø on the 28th of January this year. And I would say it's an expedition in itself because we had a 5-week-long voyage without any light, basically. And it's a bit spooky, actually, because you don't really know where you are. It's completely dark. The only light you have are these flashlights from the ship. And here we actually see a lead. And this is basically the main types of channels you can travel in so far north, because Polarstern was at 89 degrees almost north, and it had never been done to break with a normal diesel engine icebreaker through the wintertime ice to go that far. So actually we had to break a record to comply with the general planning of Mosaic, and that was not trivial at all. So here is a little bit of an impression. Ah, no, this doesn't work. Let's see. Just try to click like this. Yeah. So this is a present we gave to the crew of the Granitsin with whom we traveled there. That's drone shots. It's actually professionally made by the film team that was with us. And we were supposed to travel only for 2 weeks, but the voyage took 5 weeks. And we almost ran out of fuel, and it wasn't sure at all if we would arrive. So now imagine all these scientists eager to do their science on board, and you don't know if you can get there. So we had a couple of very, let's say, stressy days where we had to deal with. This was already the first type of challenge. And yeah, here you see how the ship is moving back and forth, trying to break the ice. We tried that for a couple of days and didn't move more than 10 kilometers per day, so you could easily walk that, but expended a lot of fuel. So then we had to change strategy and just wait until the pressure on the ice would be released and you have the lead opening and then travel through. And there is actually where the remote sensing comes in, because we requested special satellite images so we would understand where will leads be forming or where have they formed, direct the ship in that direction, and then go like this. We did ice watch on the bridge to entertain ourselves, so every hour to understand what's the sea ice surface like, the ice types, etc. So we could learn a little bit and take advantage of that situation. And it was also a good occasion to do good team building in that time, which we needed because we would spend much more time together than originally planned. Now, I was head of the atmosphere team, 15 people who conducted the atmospheric research, and this is just a short or brief schematic of what we were after. So we had people looking at the larger scale dynamics that's indicated at the top, and then in the bottom left you see the little wiggles for the turbulence, so that's very small scale air mass movement. Then we had lots of interactions that we studied between the ocean, the sea ice, and the atmosphere in terms of radiation, but also in terms of chemical fluxes. And so we actually needed a lot of different expertise to do that, but also importantly, I mean, ideally you want to staff your projects with more people than you can have on board. So helping each other was an extremely important component in that respect as well, to get all of this done. And I just want to give you a bit of an impression of what were the types of installations we had. So this is on the ship. We had this whole container deck, and there were lots of remote sensing instruments, radars, sodars, lidars, you name it. And then we also had a number of laboratory containers to measure the chemical and the chemistry and microphysics of the atmosphere. And that's me standing on the Swiss aerosol container there. And also very importantly, we had these balloon launches every 6 hours, every day. So that obviously requires the whole team to take turns. And we had a couple of intensive observation periods where we launched balloons every 3 hours. So that's quite a bit of a commitment. And then we had lots of installations on the ice as well. So you see Miss Piggy there. That's a tethered balloon. The name comes from the reddish pinkish color. And you see two sondes on it. In this case, it's for particle measurements and for ozone measurements. That worked really nicely. Sometimes we had to schedule the ascents of Miss Piggy with the UAV flights, which is just under Miss Piggy, because we needed to coordinate the airspace. And the UAVs, they carried a really small payload. So to understand atmospheric state parameters, relative humidity, temperature, some radiation parameters. And the interesting thing was when we started with the UAV flights, we had for the ground station control fixed coordinates. So we would leave at coordinate XY and call the UAV after half an hour back to come to that position. What we didn't think of in the first instance is that we're moving, we're drifting. It's a drift experiment. And then the first time the UAV actually crashed in a very different place where we didn't expect it to crash. So we learned very quickly after that loss, and then had to readjust these coordinates, which made the whole process a bit more tricky, but we could cope with that easily. Then in the top row in the middle, you see rocket traps, and this is where actually Martin science and the atmospheric science come together quite nicely. So they collect blowing snow, and then we can understand on the one hand how much blowing snow that is, but on the other hand also what are the chemical components, so the aerosol particles that form each of the snow crystals. And these actually became fish traps after a while because they ended up in a big lead and went to the ocean floor. So we lost them, but we had spares to put up. Below that, you see a 23-meter mast, which we put up to measure different atmospheric state parameters at different heights. And then there was the 11-meter tower, which is a bit more sophisticated. You see all sorts of installations there. And this was placed in Med City, our main go-to location on the ice. And now I just wanted to show a little bit of data. So it's nothing fancy. On the top, you see wind speed, at the bottom, temperature. And focusing on the wind speed first, you see there is all these spikes, and that basically tells you that the late wintertime Arctic is actually a very stormy place. It's not very pleasant to be out then because it's not only cold and you have the wind chill factor, but also it's lots of blowing snow. You don't see very much, which is very tricky for bear guarding. But on the other hand, I think we have pretty great measurements from all these occasions. And I think we can advance quite a bit on understanding all of these dynamics. And at the bottom, you see the temperature. When we did the exchange, we had temperatures near minus 40 degrees C. So that's in early March, which was tricky because cranes don't work. So lots of the logistics exchanging between ships and so on is not that trivial in such conditions. And then you see through March and the first half of April, temperatures were around minus 30 plus minus. And then you see this time period here, that's 42 hours, where the temperature rose from minus 28 to minus 1.3 degrees C. So that's more than half a degree per hour. This is tremendous. And that occasion was that there was a warm air mass intrusion coming from the south, bringing warmer and moist air masses. You could see the clouds from the horizon approaching. And then after that, you see there is a second warm air mass intrusion, and then basically you have a step change in the temperature. So that was a transition between winter and spring in this year. And I would never have imagined that it's so drastic. And speaking for the chemistry of the atmosphere, that completely changed. So we see a winter Arctic northerly regime, and then we see a more springtime or summer regime, and the chemistry is completely different. So that's quite intriguing. And just one thing to briefly mention, because you might have heard about it, that there was a very strong ozone depletion. You always have ozone depletion at the ground in springtime in Arctic, which owes to halogen chemistry. But this time also we had very strong ozone depletion in the stratosphere. So you see on the left graph the percentage loss of ozone, which is very high at around 18 kilometers. And this is where you normally have the highest ozone concentration. And then on the other panel on the right, you see our ozone sondes that were launched from Polarstern. And so between 17th of March and 17th of April, you see around the 20 kilometers that the colors are a bit yellower. So this is where there was a really strong depletion, which we could observe from the ship. And just to give you a quick idea what like Team Atmosphere did in these couple of months that we were on the ship, maybe the most impressive number is the second box on the left side, which says distance MC, which is Met City, traveled relative to the ship 1.4 kilometers. So it means the relative movement between the ice and Met City, which was sometimes only 500 meters away, was 1.4 kilometers in 3 or 4 months. So that's quite impressive. We flew the drone more than 51 times. Miss Piggy did more than 30 ascents. What I found very interesting is, so we had a LiDAR that just pulses the laser light, and you can always see this green light, but if you count the number of seconds that the laser was on from beginning of March till the end of May, it's only 1.31 seconds. It's just incredible. I mean, this is extremely short. So now, but you see this light constantly. So that's something very, very interesting. And maybe another number to highlight, the total number of atmospheric instruments that we operated during that time was 186. So you see the sort of commitment that there was. And a different type of statistics, that's our logistics special, because much of being out there is actually not only getting the data, operating your instruments, but it's actually maintaining everything. And you see here how we're rescuing a cable. And we had these movements of the ice a lot, which you will see in the next slide. And that means all these power cables also, they might be under tension or they end up in a ridge. So you constantly need to be out there and see how you deal with that. And what it sometimes means is you just need to remove them. There is no way, because the ice is too dynamic, which also meant for us, we had to carry more than 1.2 tons of diesel or gasoline to Met City to operate the infrastructure on generators. And we did that by hand or with pulkas, so not with skidoos. So that's quite a bit of work. And yeah, so we had lots of fun also going to Met City from the ship, because every time the sea ice moved, we had to find a new way. So we came up with this rough number that we had to come across cracks, ridges, and leads roughly 90 times. So that's quite a large number, but you'll see why in the next movie. And then you also see that installations taken out by leads, that's the rocket traps or fish traps that fell to the ocean floor. We had to move Droneville, which was basically the tent from which we flew the drones 3 times because it always ended up near cracks. So that was quite dynamic, and we had to deal with a lot of these challenges. And see if this also doesn't start like this. Just started like this. So this is now a camera which was on top of Polarstern, and it took every 20 minutes a picture. You see a ship that just left. That was us exchanging with Martin's group. This is exhaust when you see this fog, and now you already see how the ice starts moving. So basically every morning you wake up and the landscape is different. That also means you cannot plan for very long in advance. You need to get up and see what's the situation, and then you know, oh, I can go to my measurement site, or I cannot go to my measurement site, or I need a float, I need something else to get there. And this is also why the logistics team was so important to help us do that. Yeah, you see some power lines there, the orange lines on the right, which will go away at some point. You you see a tent, so that's a Droneville tent there, which we had to move. And yeah, I think it's just fascinating to live in a place where the surface is constantly changing. I think it's quite unique. There's not many locations on Earth where you experience that. Yeah, and there you saw this big crack that Martin showed in Amy's image. At that point, we had to leave anyway, but it was a day before we finished taking down all the installations from the ice, so that made it a bit challenging. And yeah, thank you very much for your attention. And we're happy to answer.
There are 2 questions from the chat. Maybe I can start with that. One to both of you from Jean Dalbec. Do you know if there will be some kind of synthesis report bringing results from different groups together? And one from Patricia Holm to you, Julia. What measures did you apply to avoid contamination by your own activities and your colleagues' activities?
Yeah, I can take the second question first. Yeah, so actually that we had a special working group to think about that, because the impact we could have, I mean, obviously is exhaust from the ship for atmospheric chemistry, but you have a very similar issue for the oceanographers, because there's gray water from the ship. But you also have the issue during polar night where you have light pollution. So we had a dark side where Martin can probably comment much better, because when we were there it wasn't dark anymore. But that was very far away from the ship, so to avoid that the ship light would influence any microorganisms there. For the gray water, they had a special treatment, and they tried to release it at a point in time when it was most convenient for the oceanographic measurements. And in terms of using skidoos and helicopters and generators on the ice, we always try to be very aware of what are the chemical measurements on the ship. But obviously, in the end, you can never prevent that completely.
Yeah, I can add maybe, so we sampled black carbon at different sites to measure the impact of pollution by the ship. And we also sampled microplastic in the snow. So we have then some idea how polluting we are there. And the first question, sorry.
The synthesis report.
Yeah, there will be a synthesis report. It should be as soon as possible, but we are working on it.
So just for curiosity, you mentioned there's movement all the time. So the ship moves relative with the ice, but also relative to the ice. So how much corrections did you actually have to do to stay in a position, or was it completely free floating?
Mm-hmm. Yeah, that's a very good question. When we were there in the beginning, when the first big crack happened, the ship actually detached partly from the flow. And this is actually a dangerous business, because there is lines keeping the ship to the flow. So you put ice anchors in, and they are then very much under tension. And when they snap, that's pretty terrible. So luckily that never happened when somebody was on the ice. But that means or we actually had to rebuild these lines and put in new ice anchors, and we almost ran out of ice anchors. And at some point, we couldn't keep the ship close enough to the flow anymore, which was quite detrimental to the oceanographers who wanted to run CTDs through an ice hole in the flow from the ship, because the crane only goes that far. And then we had to use different means. And so we actually invested a lot of time in keeping the ship in position. We then had to turn on the main engine and reposition it. And at some point, we also thought about actually changing position completely to find a more stable area, which then wasn't necessary anymore. But I think the captain and the crew, they invested a significant amount of time of actually guaranteeing that we can get on the ice every day.
I still have questions from the chat, if it's okay. No, I don't know.
No,
that's
I'm
fine.
sorry, but I think we're running quite late. So maybe if you don't mind forwarding the question to Julia or Martin or both, we can take it. And I'm very sorry to cut you a little bit, because it is fascinating and it's an amazing experience. And I think we're all really impressed by those images. It's given that everybody's been stranded for so long, it's really good to see that there is something out there as well. So thank you again.
Thanks everyone.
So maybe, okay, I will, so the next part of our agenda is actually, and we will see how we manage to keep it interactive, was to give you the opportunity to have a forum where you can present either developments or new projects in organizations that are related to the work we're discussing here, or to your own field work or things of general interest for this community. Now, obviously in a blended format, we will see how this works, and I hope we still manage to have a little bit of interaction in spite of this, but also we're running slightly late. So first, we have 3 persons who flagged that they would like to mention something here. And so Andreas Vieli would be the first one who would say a few words on behalf of the SKPH, the Commission for High Altitude Research, High Altitude and Polar Research from the SCENAT. So please try to keep it short.
Thank you, Daniel. Oh. Yeah, I'm standing here as a representative of the Swiss Committee for Polar and High Altitude Research, and I would like to introduce you a little bit what we actually do and what we stand for. Maybe the next slide. So, so we basically represent polar science and high altitude science in all of the committees, international committees, and for Switzerland. So I ask SCAR also in the Arctic Council. We basically represent the people there or look for representatives. Then we're really the lobbying group for polar science and high altitude science. And we try to promote this type of science and also early career researchers and research. And one part in there is, for instance, the prize we give out every year, which is the Prix de Kervin, which is the prize for, in one year it's polar science, and in the other year it's for high altitude research. And I come back to that. And basically we are a bunch of senior and junior scientists, about 17. There's also some representatives from, for instance, from the government, Swiss government actually. And what we are not is a funding agency, so our budget is extremely small. We use that mostly for the early career scientists and the Prix de Kervin. And we don't fund any projects as such. And we are also not part of SPI although we have some representatives in the Swiss Polar Institute, and they also have representatives in our commission, which I think is important. And so it's important to basically coordinate and exchange things there. Next slide. So this prize we give out every year, the Prix Dequervin, is named after one of the early polar scientists of Switzerland, Alfred Dequervin, and his group in 1912, they crossed basically Greenland, and it was one of the first real scientific expeditions. And in honor of him, we have this prize we give out to early career scientists. That could be PhD projects, excellent papers, and so on. This year, the prize was for polar science, and it was given to, now I have to read it out again, Leo Pfaffli, and she did actually, her work was about this expedition in 1912. It's a PhD work, this expedition of Alfred Dequervin. And if you haven't heard of him, and if you're still curious, for the next 2 days, there is still an exhibition just down by the railway station in the Landesmuseum. It's not very big, but it's very exciting. And if you can't make it in the next 2 days, you can also look at it online. Due to Corona, everything is possible. So it's worth looking at it. Next slide. So every second year, the prize goes to high altitude research. So next year, it's going to be in high altitude research, and the deadline for nominations is, I think, in May. It will be sent out probably also over the SPI channels. And if you have any exciting project you want to nominate of a young researcher, then please do that. And it's the topic, it doesn't have to be, you know, just to do with high mountains in a way that you think of snow and ice. We also had prize winners which were from medicine. There's all sorts of topics you could think of. Okay, next one. Yeah, and if you're more interested, have a look at the website or ask our president, Hubertus Fischer, who unfortunately couldn't make it, the vice president, Patricia Holm, and also our acting executive director, which is Christoph Kuhl. So if you're interested, ask them as well. Thank you.
Thank you. Thank you very much, Andreas. And we are very much looking forward to hear more from this year's prize winner next spring and to hear her lecture. Thank you. I think Carla, who is the co-chair of APEX Switzerland, wanted to say a few words. And Carla, if you agree to maybe come down, that's maybe the easiest. Thank you.
So yeah, hi, okay. Hi everyone, I'm Carla, and I just wanted to present a bit APEX, which is the Association of Polar Early Career Scientists. This is an international and interdisciplinary association. So it had representation in about 7 countries and more than 3,000 members worldwide. And it has a commission, let's say, here in Switzerland that was founded by Saskia Grindeau and Martin Frosch in 2015. And me and Rebecca Guderli, who couldn't be here today, we are like currently the national committees of the affiliation here in Switzerland. So the role of APEX is mostly to bring together young scientists in polar and high altitude research, and also to promote science outreach. So in our case, we work closely with the SPI, also with the SKPG and the Swiss Snow, Ice and Permafrost Society. And what we try to do is to organize events, career events that were organized in the past, for instance, career development workshops, networking events at conference to bring the young community together. Also excursions. There was an excursion organized in Jungfrau Hoch in the past that we would like to repeat. Also APEX, in this case, when it was with Saskia, organized the first Swiss Polar Day. But we also tried to do activities in outreach, and we had a workshop, for instance, in science outreach in April last year. For the next activities, what we would like to organize, but this is something I'm still discussing with Rebecca, an event, a networking event in Jungfrau Hoch for February, but we are still working on it. Besides that, this APEX is, we are always looking for members. It's also very important. We need people to take over the association as national committees, because we both will be finished, let's say, in our PhD more or less soon. So yeah, it would be great if someone could take over. And that said, I'm gonna provide this, I brought a bunch of these flyers, so if anyone is interested, or if you could take some of them for your different universities and institutions, that would be great to promote the association. And yeah, it is bigger, so they also organize international events, international conference, webinars that you can check in the website. So it's a really good platform also to keep update with the polar research. So yeah, if you have more questions, if you would like to sign up and join us, you can just come to me. I will stay for the networking drink later. And I will leave some of these flyers also a bit if someone wants to take. So yeah, thanks a lot for the attention. And thanks for the space.
Thank you very much. Thank you very much, Carla. You can maybe give it to Nina. We will clean the mic. You're very welcome also to contact us if some of your students or yourselves would be interested in the work of APEX, or even in getting engaged into the work that they do. From the social sciences and humanities, I think we had Mirko who had announced he wanted to say something. Maybe, I'm sorry, I will have to press you to be brief. I know it's not your fault, but those who come towards the end, unfortunately, bear that burden.
So thank you very much that we have the chance to present our new research group here. So I'm Mirko Brunner from the University of Bern. I'm an archaeologist and I'm working at the Institute of Archaeological Science and the Oeschger Center for Climate Change Research. So, and today I'm here to represent our newly established research group, Humanities in Arctic Research, from the University of Bern. And the idea to establish such a research group in humanities in Arctic research came after the workshop on social science and humanities in polar regions organized by the SPI in 2019 in Neuchâtel. And now, 1 year later, we are already financed by the intra- and interfakultäre strategische Projekte of the University of Bern. And that allows us now to connect and interact within the university itself. So the humanities in Arctic research are put together out of different disciplines, such as archaeology, social anthropology, history, music science, art history, and linguistics. So because our research group is rather new, we are organizing a network workshop on humanities in Arctic research. So, and the workshop encourages interdisciplinary dialogue to foster future collaboration in this important field, both in Switzerland and also abroad. The workshop itself takes place at the university in Bern. So the workshop is basically, the aim of the workshop is basically to connect between different researchers and to establish a network in the humanities in Arctic research. So the workshop takes place next year in November. Keynote speakers are already set, but there will be also a call for papers very soon on our brand new website. And I also brought some improvised flyers today with the program on the back. So feel free to take one of these if you want to join for this workshop. And you can also contact us via the website, which is on the flyer. And feel free to contact us via the website or ask me afterwards. And yeah, so thank you very much for your attention. I hope that was short enough. And yeah, the flyers you will find here.
Cool.
Thank you.
Thank you very much. I think that's a wonderful initiative, and we look forward to your workshop. It's a great new dynamic. Do you have anything from online?
Yes, there was a raised hand by Patricia. Patricia, just go ahead and unmute yourself. Patricia, can you please go ahead and unmute yourself? She had raised her hand. Yes. But we don't hear her, huh? She's unmuted.
Can you hear me now? Can you hear me? Can you hear me now?
No,
Can you hear me?
No, she should be okay.
Can you hear me? Can you hear me? So if not, I type the message. Can you hear me?
I'm not sure. Honestly.
Can you hear me? Can you hear me?
Okay.
Can you hear me?
Can
you hear me now?
Can we use the mic? Yeah.
Can you hear me?
It obviously not. Test this.
Can you hear me? Can you hear me?
Yes.
You can hear me. Okay, thank you. Sorry, sorry for this. Yes,
Patricia? No, we cannot hear. Maybe we just really need to translate the message. Can you hear what you say? Do we have? Yes. Patricia?
You hear me. Okay, so I would like to congratulate Lea Pfeffli very, very much, because I think that's really a wonderful piece of work. And I'm really proud that she received this prize. It's a very interdisciplinary study. It's on science, on knowledge science. And I'm looking very much forward to hear herself talking about her work next year. And I wish her all the best, because she's right now on maternity leave. And I can also, as far as I know, tell you that her study will come out as a book soon. And so you can already have a look at this. It's already announced on the internet. So I'm very proud, and my congratulations to Lea Pfeffli. Thank you so much.
So
It was Patricia Holm. She's the vice chair of SKPH, congratulating Lea Pfeffli warmly. Her book is going to come out soon, apparently. She's also on maternity leave. So congratulations to her. And we all look forward to hearing her in the spring at the Swiss Photo Day. Anyone from the, anyone here in the room who would like to add something to share? Otherwise, it's always possible, obviously, to use either our social media or our regular newsletters. If you have something to announce, we're always happy to pass it on and to stay in touch. Don't hesitate to let us know. I'm sorry about the technical difficulties. I think we will close here. I would like to invite Gabriela for a few words. And from my side, I would like to thank you all also because we were over 100 on and offline this afternoon, and given the circumstances, very fast.
So I really understand that between you and the apero waiting out there in Lichthof. I don't want to make it long, but I think we have heard about very exciting research. We have heard about impressive and difficult field conditions and measurements. It's really impressive. And I think we also have heard about how much is still ahead of us, how much we still need to work on things, how much uncertainty there is still out there. So I really hope that you will connect during the networking event that we'll have right now out there. Please keep your masks on as much as possible. We don't want to be that a super spreading event. So I would really like you to keep your masks on. We need you doing science. We don't need you in quarantine. So with this, I would like to close this day. I would like to send all the greetings also to our online participants. And I very much hope that we can reconvene next year again, probably around April, for a real networking event where there will be more people again in presence and enjoy networking. So please join us outside if you feel like it in the Lichthof for a few drinks. Thank you very much. Good.